The objective of this study is twofold. First of all, we want to use the detailed data that DNS can provide to understand what is actually going on when you pump air through the wall into a turbulent boundary layer. The focus is on relatively large bubbles that are likely to be encountered in practice, and the hope is that we can simulate a sufficiently realistic situation so that the mechanism that we extract out of the data is of some relevance to realistic flows. The second objective is to use the data to gain averages that are useful in closing the turbulent equation, and therefore can help us in generate models that can actually simulate the turbulent flow with bubble injection in realistic situations. Direct numerical simulations of bubbles and turbulent channel flows or turbulence flows has turned out to be a fairly difficult problem. We, as well as a few other groups who attempted similar simulation, initially found drag increase when we put in bubbles into the turbulent flow, but we have now conducted a large number of simulations which allowed us to cast a little bit of a light on what is going on. I've selected to talk about a set of 3 simulations here, all done in the minimum turbulence channel of imminence and mowing. The dimensions of the channel are shown in the table below. In computational units, the channel height is 2, it's pi long and pi over 2 wide. The turbulent Reynolds number, based on the wall variables, is 135, which corresponds to half the channel height in wall units. We have used 16 bubbles, 8 at each wall, initially put in an almost regular array, although the array was perturbed a little bit. It's about a bubble diameter away from the wall. We run them for sufficiently long time so that the bubbles have modified the turbulent flow significantly. To avoid the initial transient, so that we don't have to follow the motion of follow the transition of the flow to turbulence, we actually received turbulent data from the Brown group that we have used as initial conditions. To carry out the simulation, we start with the turbulent flow that we have obtained from the Brown group, and we simply put bubbles into the flow at time 0. So for a little while the flow has to adjust to the turbulent flow or the presence of the bubbles, but after that the flow and the bubbles interact fully by the solution of the Navier-Stokes equations. This slide shows 3 runs, one with flow without bubbles, both at an early time in the left column and at a later time in the right column. The flow without bubbles is at the top, and while the vertical structures have evolved, they have not changed in a fundamental way. The middle frames are from a simulation where the bubbles remain relatively spherical, and the vertical flow has certainly changed from the early time on the left to the late time on the right, but the vertical structures are somewhat similar. In the bottom frame, where the bubbles are most deformable, at the early time there are relatively little changes to the flow, but at the later time there's actually been a significant decrease in the streamwise vorticity. The Weber numbers are selected in such a way that the highest Weber number corresponds to bubbles that deform significantly when they are a little bit away from the wall, so that they're still subject to shear, but they still stay together when they get very close to the wall. The lowest Weber number, on the other hand, corresponds to bubbles that remain essentially spherical except when they're very close to the wall. In this slide, we're looking at 2 bubbles close to the top wall. The bubbles are shown in a plane perpendicular to the flow, and the color corresponds to the streamwise velocity. So red corresponds to the fast-moving flow in the center of the channel, and blue is the nearly stationary flow next to the wall. The quantity that we are most interested in is the wall drag. In this figure, we plot the average wall drag for 4 runs, both flow without bubbles as well as flow with bubbles with 3 different Weber numbers, both on the top wall and the bottom wall. The solid line is the flow without bubbles, and even though there are some fluctuations, for the most part, if we simulated long enough, we would expect that the drag to average out to approximately constant. The drag varies because we specify constant through flow, and therefore as the flow structures change, you would of course expect the drag on the wall to change. For the least deformable bubbles, the dashed dot line, we actually see a significant increase in drag for both walls. At the top wall, the drag decreases eventually, but on the bottom wall, the drag actually stays high throughout the simulation. For the most deformable bubbles, on the other hand, the dotted line, there is, however, significant drag reduction. Indeed, there's a drag reduction that continues until the very end of the run for the top wall, where it actually, as I will show you a little bit later, it increases slightly because all the bubbles are leaving the wall. On the bottom wall, the drag is still decreasing, and at the end of the run, we see about 20% drag reduction for this particular case. The intermediate Weber numbers are somewhat in between. We see sometimes increase in the drag and sometimes a decrease. In this slide, I have plotted the average velocity profile averaged over planes parallel to the wall for the no flow and for the flow with the most and least deformable bubbles. The velocity in the middle of the channel actually hasn't changed very much, and indeed near the walls we don't see much difference unless we blow up the velocity profile or enlarge the velocity profile, as I have done at the sides of this graph. Since the drag is reduced at this time, obviously the slope of the velocity profile has to be smaller for the velocity for the case where we have less drag, and that is indeed what we see. However, the slope is relatively, the difference in the slopes is relatively small, and therefore we really have to look very closely. Overall, the velocity profile has not changed very much with the addition of the bubbles, even in the case where the drag is actually reduced. To understand what changes the bubbles cause in the flow and what flow changes lead to drag reduction, we have looked at several quantities. In this slide, we plot the Reynolds stresses, the U prime, V prime Reynolds stresses, the wall normal velocity fluctuation and the streamline velocity fluctuations at two different times. We also show the relative size of the bubbles with solid circles to give you some indication of the relative size of the bubbles compared to the channel. At the first time, there isn't very much changes in the Reynolds stresses, but in the later time, the bottom slide, we do actually see that there's a significant or some reduction in the Reynolds stresses that corresponds to the most deformable bubbles, therefore suggesting that it is the reduction in turbulent transport toward the wall of high-speed flow toward the wall that causes the drag reduction. However, the highest Reynolds stress is actually for the flow without bubble, and there isn't much change in Reynolds stresses for the flow of the less deformable bubble, which actually leads to drag increase. We see the same thing in this slide, where we have plotted the integrated value of the absolute value of the Reynolds stresses, the U prime, V prime Reynolds stress that I showed in the previous slides versus time. Again, it's clear that the deformable bubbles, so the most deformable bubbles, have the lowest Reynolds stresses or coincide with the lowest Reynolds stress in the flow. But again, certainly at early time, it's the flow without bubbles that has the highest Reynolds stresses, and there's no clear correlation with an increase in drag on the wall and increase in Reynolds stresses. So while the decrease in Reynolds stresses for the most deformable bubble certainly is suggestive of what's going on, there's not a direct correlation between the Reynolds stresses and the wall drag. In this slide, we take a closer look at the effect of the bubble on the vorticity. In addition to the bubbles, we plot the streamline vorticity colored according to the rotation of the vortices. So yellow rotates one way, blue rotates another way. In addition to the streamline vorticity and the bubbles, we plot the wall shear stress on the bottom wall below each figure. Obviously, red is high shear and blue is low shear. It is clear that the presence of the bubbles has actually modified the streamline vorticity significantly. In particular, it's a lot smaller than in the case without bubbles. The plot of the streamline vorticity in the last slide obviously suggests that there's a strong relationship between the streamline vorticity and the wall drag. To examine that a little bit closer for the case of the most deformable bubbles where we see strong drag reduction, in this slide we plot the entropy, the vorticity squared, integrated over the cross-section of the channel, actually over the total channel, versus the reduction in drag. And there's almost a straight line, and as the streamline vorticity goes down, so does the wall shear. In addition to the 16 bubble simulation, which I've been showing you, we have also plotted a few data points from a simulation with only 4 bubbles, and indeed we find that as the vorticity is reduced, the same relationship holds.